Okay, let's start. So welcome to today's webinar. Welcome to the first central exercise session for the course Mathematics 2. I hope you can all hear me. And I hope you can all see my screen. So I'm going to mainly use the iPad screen as you're used to from Mathematics 1. We projected this onto the wall. Let me give you a quick introduction first. So the idea here is, again, to walk you through some typical exercise problems. You all had a look at the sheet, hopefully. You all had a look at the videos. And now we're going to discuss the central exercise sheets, central exercise problems, to give you an example of how you could approach things, and also to give you the opportunity to ask questions. As you've probably read, there is a live chat available during this session here. So if you haven't done so, you should open a browser window and log into chat.tum.de. And there is a channel that is called MA9714. That's the module number for this course, -CE for Central Exercise Class. So we monitor that live chat during this class. If you have any questions, please just ask them there. And we'll hopefully be able to answer some of your questions on the air, or maybe in chat if they're just small minor questions. Also, if something doesn't work as it should, then please just post to this chat channel and we'll hopefully be able to repair things if they break. First thing that broke already, for some reason, there is no option to stream this thing to YouTube. So the idea was to have a live stream to YouTube just as a backup if something goes wrong, or if you don't have the opportunity to log into Zoom. Unfortunately, this doesn't seem to work anymore. It did work yesterday when I tried that in the evening, but somehow the option is gone. However, we will record this session here. So it will be available after the session ends. I'll put a link to the video on the Moodle page. It'll just be some time because I have to edit out the beginning and the end, obviously. So just in case you're going to ask questions on the air, please be aware of the fact that this is also going to be recorded. The chat channel, of course, is not going to be part of the recording. So feel free to ask anything that you want there. Also, on the chat channel, you can ask questions or post suggestions throughout the week. So if you have anything, if you think anything should be discussed on the next central exercise session, then please just post to the chat channel whenever you get a chance, so that I can incorporate this during my preparations of this session. Just to mention that as well, there's also another chat channel for this course, MA9714 General. That's meant for any questions, any ideas, any suggestions you might have, even if they're not specific to the central exercises. So please also make use of that one to communicate to me and to the team. Okay, for the chat, there is a co-host that is moderating this chat. So Eileen Karlsson will have a look at the chat, see if she can answer your questions right away, or otherwise direct your questions at me, and I'll give her a chance to introduce herself.
Okay, so hello. Maybe you see my video. My name is Eileen Karlsson. I'm a PhD in math here at TUM, and I'll be one of the people doing the exercise class for this course, and I'll be the moderator today, at least.
Okay,
yeah.
Any problems yet? Any questions?
So there's someone raising their hand, and so maybe we should settle how they will ask questions, because you will have to unmute them to have them talk.
Okay, so I'd say for now we just try using the chat. Ask your questions there. If it's better to explain on the air, if you'd like to actually speak live on the air, then just please let us know in chat and let us know who you are. And then we can give you a chance to tune into this webinar here. Okay?
Yeah, sounds good.
Good. So I guess we get started then. I'll give you a chance to ask your questions after each of the problems that we have on the sheet. So whenever there's something coming up, please don't hesitate to post a quick question to the chat channel, okay? Good. So let's get started then. You all have a look at sheet number 1. Main topic of sheet number 1 are differential equation systems, and motivated by differential equation systems. One thing we want to be able to do is diagonalize matrices. You hopefully remember basis transformation from the first semester. And here's an application of basis transformation. So back then we just got a basis and we were asked to transform a matrix to that basis. Now the question is, how can we actually find a clever basis? And clever in this case means a basis where the resulting matrix is diagonal. And in the first week, the videos were discussing how to do that and hinting a little at when this might actually be possible. It's mainly the topic of the second week then. So in the exercises here, we are mainly discussing how to do that. Basically, you need to know the concepts of eigenvalues and eigenvectors and how to compute them. And this is going to be the topic of the first 2 central exercise problems. And then there's going to be a third central exercise problem that applies this technique to actually solving a simple differential equation system. So let's start at the beginning. C18. So in this case, we have 2 matrices. We have 3 vectors that are given. And we want to determine which of these vectors are eigenvectors of the matrices. Now, just as a little reminder, oops, sorry. That's much better. So as a little reminder, to see if a vector is an eigenvector and what the eigenvalue is, what you do is basically you apply the definition of an eigenvalue and an eigenvector. So what is that definition? Remember, you have a matrix A. And if there is a vector V that is not the 0 vector, but such that A times V basically yields a scaled version of that vector V. So some lambda times V. Then V is called an eigenvector of A, meaning A maps that vector to a scaled version of itself. And the corresponding value, lambda, is called an eigenvalue of A. Okay, and keep in mind, V must never be 0, because if we allow 0, then this equation is true for every lambda that you want. So that's a pretty boring case. We don't want that. On the other hand, a lambda may be 0. So an eigenvalue of 0 is completely okay. Okay, so that's the definition of eigenvalues and eigenvectors. Now what we do in this first exercise problem is we check in which of the vectors that we are given are eigenvectors and which are not. And we are determining their corresponding eigenvalues if they are eigenvectors. So let's start with part A. The matrix that we have here is given by 1, 3, 3, minus 2, 8, 6, 1, minus 3, minus 1. Now we have to check the vectors v1, v2, v3 for being eigenvectors or not. So what we do is we just compute C times v1, C times v2, C times v3, and then see what the result is. So for C times v1, let's have a look at that. That is 1, 3, 3, minus 2, 8, 6, 1, minus 3, 1, times v1, and that is the vector 1, 2, minus 1. So if we just compute this matrix vector product, now what we get is, let's see, first row is 1 plus 6 is 7 minus 3, that's 4. Second row is minus 2 plus 16 is 14 minus 6, that is 8. And the third row is 1 minus 6, that's minus 5, plus 1, that's minus 4. So that's the result of this multiplication here. Another question is this a multiple of the vector that we put in? So is this actually some lambda times 1, 2, minus 1? And if you look at that closely, it's easy to see that this is actually just 4 times this vector here. So V1 is actually an eigenvector of C, and the corresponding eigenvalue is 4. Okay, so V1 is an eigenvector of C. With eigenvalue 4. Okay, so that's how you solve this kind of questions here. And let's just do that for the other vectors as well. So we have to compute CV2 as well. That's the same matrix here. Just write that down again. And then V2 is the vector 0, minus 2, 2. Computing that product yields in the first row, that's a 0. In the second, we get minus 16 plus 12. That's a minus 4. And in the third row, we get 6 minus 2. That is a plus 4. So again, you can see that we get a multiple of the vector that we just put in. And this time, it's 2 times the original vector, 0, minus 2, 2. So V2 is again an eigenvector of C, this time with eigenvalue 2. And once more, CV3, the last one here. So V3 is the vector 3, minus 1, 2. And that product is, let's see, 3 minus 3 plus 6, so that's 6. Then we get minus 6, minus 8, plus 12. That should be minus 2. And finally, 3 plus 3 is 6, minus 2, that's 4. And again, the question is this a multiple of the vector that we started with? And again, the answer is yes. The eigenvalue is again 2. Okay, so one more eigenvector here. So V3 is an eigenvector with eigenvalue 2. And what you can see here is that there may actually be eigenvectors, different eigenvectors for the same eigenvalue. And in fact, not just different, but also linearly independent. Yeah. So in this case, for the eigenvalue 2, there is 2 linearly independent eigenvectors. And of course, every scaled version of an eigenvector is an eigenvector once again. So for example, if we have this one here, let's see if you can see the pointer. If you have this one here, this 0, minus 2, 2. If, for example, I would be using 0, minus 4, 4 instead, that would, of course, again, be an eigenvector for the same eigenvalue. Okay, so before we proceed to the next problem or the next exercise on this sheet, part B. Is there already any questions?
So one question just arrived. How do you exactly calculate the result of the multiplication of the matrix C with the three vectors V1, V2, and V3?
How do I calculate the result of the multiplication? Okay, I'll try to make this a little more explicit in part B. That's the only question?
And then
so
there's
far?
typing, but
so I'd say let's proceed to part B then first and see if there are more questions afterwards, okay?
yes.
Good, thank you. So part B, basically the same thing once more, just with a different matrix. So this time we have the matrix D, that is 4, 0, 0, and there's 9, -2, -3, -3, 0, and 1. And the problem is the same. We need to determine whether V1, V2, V3 are eigenvectors of this matrix, and if so, what the corresponding eigenvalue is. So we're doing the same thing. We're trying to compute D times V1 first. So let's write that down first. The matrix 4, 0, 0, 9, -2, -3, -3, 0, 1. And V1 again, that is 1, 2, -1. Okay. To compute that product, let's make this explicit one time. What we're doing is we are using matrix multiplication. So we have here a 3 by 3 matrix, and here a 3 by 1 matrix, 3 rows, 1 column, or 3 rows, 3 columns for the matrix D. If we are doing matrix multiplication, then the entries of the result are always composed by 1 row of the left matrix and 1 column of the right matrix. So the right matrix only has 1 column this time. And the result will have as many rows as the left matrix and as many columns as the right matrix. So we get 3 rows because D has 3 rows, and we get 1 column because the vector has 1 column. Okay? So to compute the entry in this position here, 1, 1, we've taken the row from the first row from D and the first column from the right matrix, which is in this case just the vector, and we're computing the scalar product. So we're computing 1 times, well, let me mark this first. What we do here is take this row, we take this column, and we're computing the scalar product. So we compute 4 times 1, which is 4. Then 2 times 0, well, that is 0. And then -1 times 0, which is again 0. Okay? So this entry is 4 plus 0 plus 0, that's just 4. And we can do the same thing for the other rows, and if we had a matrix on the right-hand side, for the other columns as well, to get the final result. Let's switch the color here. So for the second row, for example, what we do is we compute 1 times 9, that's 9. Then 2 times -2, that's -4. So 9 minus 4. And then -1 times -3, that's +3. So the result here is 9 minus 4 plus 3, that should be 8. And once more for the last row here. So -301, scalar product with the vector, that's 1 times -3. That's a -3. Then there's 2 times 0, that's a 0. And finally, -1 times 1, that's a -1. Okay, so the result is 4, 8, and -4. Okay, and to see if this is an eigenvector, we just compare it to the 1, 2, -1 that we started with. And we can easily see that this is 4 times this vector here, okay? So V1 is an eigenvector of D with eigenvalue 4. Okay, I hope that helped to clarify how this matrix vector multiplication works. Good, let's do all the other two as well. So dv2, again, the matrix D is 4, 4, 0, 0, 9, -2, -3, -3, 0, 1. And V2 is 0, -2, 2. So the result here is, well, the first row is just 0 plus 0 plus 0. The second row is 0 plus 4 minus 6, that's -2. And the last row is 0 plus 0 plus 2, so that's 2. But obviously, that's exactly the vector that we started with. So this is, again, an eigenvector, this time with eigenvalue 1. Okay, so V2 is an eigenvector with eigenvalue 1. And finally, let's see dv3. Again, D is 4, 0, 0, 9, -2, -3, -3, 0, 1. And V3 is 3, -1, 2. And the result here is 5 times 3, that's 12. Then we have 3 times 9, that's 27, plus 2, that's 29, minus 6, that's 23. And then -9 plus 0 plus 2, that is -7. So again, is that a multiple of the vector that we started with? And if you look at the first row, for example, we have 12 here, we have 3 here. So the only possible multiple would be 4. But that doesn't work with the other 2 rows that we have here, okay? So this is not any multiple of the vector that we started with. So this means V3 is not an eigenvector of D. Okay, so that concludes the first problem. Let's again see if there are any questions.
So one that got answered, but I still think it makes sense to say. So if you rescale an eigenvector, that still gives an eigenvector, but the eigenvalue is always the same because you rescale on both sides.
Mm-hmm.
Yes, so that was just a clarification, and you already said it.
Let me just write that down to be sure that everyone gets that. So if we have if you have a matrix A and an eigenvector V, and the eigenvalue is lambda, so this equation here holds, A times V equals lambda V. Then of course, if you scale V, for example, let's take 3 times V, right? Then that's the same thing as 3 times AV. The 3 is just a scalar, so you can take that any way you want. And that means the result will be 3 times lambda V, or again, you can move the 3 any way you want. Same thing as lambda times 3V, right? So 3V is again an eigenvector but the same eigenvalue applies. So the eigenvalue doesn't change. Okay, and of course you can use any scaling that you want. It's not bound to that 3. You can use anything you want here. The argument always stays the same. Yeah, so if you scale an eigenvector, the result is still an eigenvector, but the eigenvalue doesn't change. The only difference is, of course, you may not scale it with 0. Yeah, 0 is not an eigenvector by definition. Okay, anything more, Alind?
No, that was it.
That was it. No more questions about the first one?
There is one person typing, but no other questions so far. Oh, so there are infinite eigenvectors, but only limited eigenvalues.
Yes, that's right. Yeah, there are infinite eigenvectors because I can just scale an eigenvector that I have by anything I want. And for each eigenvalue, I always get an eigenvector, at least one eigenvector. So I just take any scaled version of that, and that gives me an infinite amount of eigenvectors. But usually, but not usually, but always just a limited finite amount of eigenvalues that I can have. The eigenvalues are the roots of the characteristic polynomial. And of course, I can only have as many different roots as the degree of the polynomial is. That means it's always bound by the dimension of the matrix.
Yes.
Okay. Anything else?
No, not so far.
Good. Okay, thank you. It's really unusual to do this without actually seeing your faces. We'll get used to that, I hope. So let's go on with problem C19 then.
There is one thing.
Yes.
The audio got a little bit like diminished at some point. Maybe you can move it closer, the microphone.
I can try, but I don't think it allows for a lot of motion here. See, that is better.
Okay.
I have to try using a different microphone.
Yeah, so that's a couple of people said that just now, but if there's nothing to be done.
Probably not at the moment. So if that problem persists, please just post to chat later, and I'll see if maybe I can try something else next time.
Okay.
But it seems good microphones are hard to get by these times, almost as hard as toilet paper. Okay, let's try C19. That's kind of the opposite question now. So in C19, we again have matrices that are given, and this time we are given the eigenvalues of these matrices. And the question is, can we determine the eigenspaces or the eigenvectors that belong to these eigenvalues? So let's try that. Our first matrix is -2, -3, 3, -6, -5, 6, and then we have -6, -6, 7. And we are given eigenvalues here. First eigenvalue is 1. Let's call that one lambda 1. And lambda 2 is -2. And we want to determine the eigenvectors that correspond to these. So if these are eigenvalues, then at least one eigenvector must obviously exist. The method to find the eigenvectors is to have a look at the matrix A minus eigenvalue times the identity matrix, which we usually abbreviate with E and an index for the dimension. So E3 in this case. Okay, so we want to look at this matrix. This is a matrix that cannot be inverted if lambda is actually an eigenvalue. And we want to find a vector with, let's sketch it. We want to find a vector with the property AV equals lambda V. And that's the same thing as AV minus lambda V is the 0 vector. And that's the same thing as A minus lambda E3 times v is the zero vector. So we want to find the set of solutions to the linear equation system A minus lambda E3 equals, times a vector equals 0. We want to find the set of solutions here. And that set of solutions got a name in the first semester. That is the kernel of A minus lambda E3. And this kernel is then also called the eigenspace. All right, so the eigenspace basically consists of all possible eigenvectors for one specific eigenvalue, including this time the zero vector. That's just because it would not be a linear space otherwise, and we want it to be a linear space. So everything in that eigenspace, with the exception of the zero vector, is an eigenvector. Okay, so let's try this using this example here. We'll first have a look at lambda 1 equals 1. So first eigenvalue. So we have to have a look at A minus 1 times E3. So that means we have this matrix A. Let's write that down once more. Minus 6, minus 6, minus 3, minus 5, minus 6, 3, 6, 7. And then we want to subtract 1 on the diagonal. So we're subtracting 1 here and here and here. So this is this minus 1 times E3 part. So we get minus 3, minus 6, minus 6, minus 3, minus 6, minus 6, and 3, 6, 6. Okay, I want to determine the solution of this matrix times some vector equals the zero vector. So what we do is we use Gaussian elimination. In this case, we would subtract 2 times the first row from the second one to get a 0 in this position, and we do the same thing for the third row. So minus 2 times first row here. That gives us, first row stays as it is, minus 3, minus C3. The second row becomes 0, 0, 0, and the third row is just the same, so it's also a 0 row. So that means the resulting matrix has rank 1. There's only one pivot element left. We're using this one here. And that means the kernel of A minus E3 is generated by, let's just pick 2 vectors that generate this kernel. So in this case, the third and the second column correspond to free variables. So we can choose those as we want. And then the first variable has to react to that choice. So what we can do, for example, is we can decide to put a 1 in third position and a 0 in second position. Then the first variable has to be, let's see, if we have this 0 and 1 here, and multiply this with the first row, then we get minus 3x1, minus 3 times 0, plus 3 times 1. So that first position here has to be filled with a 1, so that this vector here times this row yields a 0. Okay, and we do the same thing for a different choice of the free variables. This time we're choosing x2 as 1 and x3 as 0, so that we can be sure that the 2 solutions that we get are linearly independent. And this time we have to choose x1 as minus 1, so that we get minus 1 times minus 3 is plus 3, plus 1 times minus 3 is 0, and then 0 times 3. That stays 0. Okay, so this is a basis for the eigenspace then. It's a basis for the eigenspace, and we denote this eigenspace by eig of the eigenvalue. So this is eig A of 1. Okay, two linearly independent eigenvectors for that first eigenvalue, and for the sake of completeness, let's do the second one as well. So lambda 2 is -2. To compute the eigenspace for -2, we have a look at the matrix A minus -2e3. So that is the same thing as a plus 2e3. Be sure not to confuse the signs here. So that means we add 2 on the diagonal and we get 0, -6, -6. Then it's a -3, -3, -6, and 3, 6, and 9. Okay, this time we don't have a pivot element here in position 1, 1. So first thing we do is we get pivot element here, a non-zero element. So for example, we just swap the first 2 rows to do that. So that yields -6, -3, 6, 0, -3, 3, and -6, -6, 9. And then we can start elimination by just subtracting the first row from the third. And that yields -6, -3, 6, 0, -3, 3. And here we get -6 plus 6. This is 0. -6 plus 3 is -3. And 9 minus 6 is +3. So next step we do is we subtract the second row from the third one. And that will yield, well, first row stays untouched. Second row as well. Just copy that one. And the third becomes 0, 0, 0. Okay, so we can again solve this system. In this case, we have 2 pivot elements here and here. And we have 1 free variable in the third column. So let's write this down explicitly just to give you a quick reminder of how this works. Third variable is free. The second row gives us the equation -3x2 plus 3x3 is 0. And we can solve that for x2. So x2 is equal to x3. And finally, we use the first row, -6x1 minus 3x2 plus 6x3 equals 0. And we solve that for x1. And what we get is x1 is, let's see, -1/2 x2 plus x3. x2 is the same as x3. So if we substitute that into this equation, we get -1/2 x3 plus x3, or just 1/2 x3. Okay, and that means the solution that we get is the eigenspace corresponding to the eigenvalue -2. That is spanned by, let's see, we're free to set x3 however we want. So in this case, to avoid fractions in the final result, what we do is we set x3 to 2. Then we get a value of 1 for x1 and no other fractions. Okay, so we'll start with that 2 here. x2 is equal to x3, so that's also 2, and by this last equation here, x1 will then just be 1. So 1, 2, 2, and that is a basis for this eigenspace of A for the eigenvalue -2. Okay, so that's how you determine eigenspaces. What questions are there?
Now there are a couple of questions. For the already at lambda 1, someone asked, why is the rank of the matrix 1?
Why is the rank of that matrix 1? Well, if you have a look at this last matrix here, I hope you can see my pointer, can you? Aline, can you see that
Yes.
pointer? Okay, great. So if you look at this matrix here, then you can see we have this one non-zero row here with one pivot element here, and there's 2 zero rows. So no pivot element in these rows. Zeros can't be pivots. So we just count the number of pivots. That's the rank of the matrix. And Gaussian operations don't change that rank. So the original matrix, this one here, then also had rank 1. In contrast to that, if you have a look at this matrix here, there's one pivot here, and none in the third row. So we have 2 pivots. The rank of this one is 2. Okay.
And then the next question, how do we know that the eigenspace contains 2 vectors? So that was also for lambda 1.
Was also lambda 1. So how do we know that the eigenspace contains 2, well, actually contains infinitely many? It's spanned by 2 linearly independent vectors. So the dimension is 2. And we do know that once we have, just a minute, sorry. We do know that once we have this matrix here. So at this point, we can see that the rank here is 1, which means we have 2 free variables, right? Number of columns minus the rank is the number of 2 free variables. So the dimension of the kernel, or of the solution space more generally, of that linear system is a number of columns minus the rank. So in this case, 3, that's the number of columns, minus 1, that's the rank. So we get a 2-dimensional solution space. And that's the dimension of the eigenspace in this application. So we get 2 linearly independent eigenvectors because there's a basis with 2 elements. Okay.
And then there was a question, what if you instead plug in x3 equals 1, x2 equals 1 for the first vector, and then you do 1, 0, 0 for the second vector? So it's still, they all have pivots.
Right?
Yes.
Can you repeat the question?
So basically 0, 1, 1, and then 0, no, and then 1, 0, 0 instead.
So let's see, instead of this, you want to do 0, 1, 1, and
1, 0, 0.
1, 0, 0, like this. Okay, so as you can see, this one here, this would also solve the equation system, so that's fine. We can use that as a solution. This one here would not. So the scalar product of this with the first row is -3. That's not 0, so that's not a solution. But of course, you could start with the first one. Let's forget about this one here. You could start with the first one with this 0, 1, 1, and then try and find another one that is linearly independent of that. So once I started with this, I could then, for example, choose 0, 1 again. And have a 1 at the first position, like I did with my first vector. And these two would then also be solutions that are linearly independent. So that's a perfectly valid basis as well. Yeah, so whatever choice you do for your free variables is basically up to you, as long as you get a non-zero result. That's probably what happens here in that case. If you start with 0 and 0 for x2 and x3, then the only possible choice for x1 is also a 0. And that does not give you an eigenvector, and also no vector that you can use as part of a basis. Yeah, so that doesn't work. Any other choice will do, as long as you make sure that whatever choice you make for those two results in 2 linearly independent vectors. And that is basically why I choose 0, 1, and 1, 0, because this already ensures they will be linearly independent.
And then there was the last comment wanting to have more explicit how you do the kernel, like how you calculate the kernel. So,
more explicit kernel calculation.
because someone hadn't had it. I don't know if it makes sense, or you can also ask them in the session on Thursday.
Yeah, maybe we just do that. I would hope that at least in part B, I was pretty explicit about calculating the kernel. If that doesn't happen, it's probably best to ask in the tutorial session on Thursday, and I'll see what specific problems you have there to be able to answer that.
Okay, that was it.
Good, thank you, great. Then let's have a look at part B. So idea is pretty much the same here. We have a new matrix, B, let me write that one down. 1, minus 1, 0, 2, 0, minus 2, minus 1, and 2. And only this time we have 3 eigenvalues, 0, 1, and 2. So 0 is a perfectly valid eigenvalue. And again, we want to compute the eigenspaces here. So let's start with lambda 1, that's 0. In this case, we just need to look at the matrix B minus 0 times E3, which is just the same as the matrix B itself. Yeah, so let's write that down once more. And then again, we need to compute the kernel for that. And to do that, we are doing Gaussian operations again. So we're choosing this as our first pivot element. We're subtracting 2 times row 1 from the second row. We're adding row 1 to the third row to get zeros in this and in this position. And that yields same first row. And then we get 0, plus 2, minus 2. And for the third row, we get 0, minus 2, plus 2. And then you can hopefully see if I just add the second row to the third, then I get a 0 row here. So first 2 rows, just copy those. And the third one then becomes a 0 row. Okay, and I'm done. The result has rank 2. So I'm getting a 1-dimensional eigenspace. And let's see, this is spanned by well, the third column again corresponds to a free variable. The first 2 correspond to these pivot elements here. So we can choose whatever we want for x3 in this case. And for example, let's just choose 1 here. So if we choose 1 for x3, then if we look at the second row, we have to choose 1 for x2 as well, because then we have 2 times 1 minus 2 times 1, that's 0. And with this choice given, let's look at the first row. We have minus 1 times 1 plus 0 times 1, that's a minus 1. So with this coefficient 1 here, we need to choose 1 for x1, so that again, this vector 1, 1, 1 times the first row becomes 0. So that's the basis for this eigenspace. And we just do the same procedure for the other 2 lambdas, sorry. Lambda 2 equals, let's do 1 next. So B minus E3. That is 0, 2, minus 1. Minus 1, minus 1, minus 1, and 0, minus 2, 1. Okay, and again, there's a 0 in this 1, 1 position, so that does not give us a pivot element here. So first thing we do is we swap a little. Let's just swap that last row into the first position because there's a 1 there, seems convenient. So -1, -1, 1. The 2 stays as it is. And the third is the old row 1. So it looks like this. And then we can just add 2 times row 1 to the second one to get a 0 here. Now we already have a 0 here. So we get -1, -1, 1. 0, -3, 0, and 0, -1, 0. Yeah, and then it's just subtracting 1/3 of row 2 from the third row to again get a 0 row. So let's leave this as it is, and the last row becomes a 0 row. And again, we have 2 pivots, this one and this one. So the eigenspace is going to be one-dimensional again. And it's going to be the span of, let's see. So again, third column corresponds to a free variable. The second row gives us the equation -3x2 equals 0. So x2 is 0. So let's set 1 for x3 arbitrarily, 0 for x2. And then we look at this first row, and if we have this 0 and this 1 already set, then what do we need to choose here for the first entry for x1 in order to make this work? Well, the answer is 0, 1 times -1, 1 is 1. And we have a coefficient of -1 here, so we need to choose a 1 for that x1. Okay, so 1, 0, 1 times -1, -1, 1 will result in 0. And that's what we want. Okay, so that's our second eigenvector. And finally, the third one, λ3 equals 2. There we need to look at b minus 2 E3. So that's -1, 2, -1, -1, -2, -1, and 0, -2, 0. So again, Gaussian elimination, we just add 2 times the first row to the second, and we subtract it once from the third. And what we get is same first row, and then a 0 here. -2, -2 is -4, and -2 plus 0 is -2. And for the third row, we get -1 plus 1 is 0. Again, -1 plus 1 is 0, and that 0 stays as it is. So we're done already. We got 2 pivots here. We again get x3 to be the free variable. So the eigenspace of, that's not A, it's B. The eigenspace of B for the eigenvalue 2 is spanned by, let's see, if we set, let's say we set x3 to 2 this time, let's see in a minute why. Because if I look at this second equation here, I get -4x2 minus 2x3 equals 0. Let's write this down. -4x2 minus 2x3 equals 0. So if I set x3 to 2, then I get -4x2 minus 4 is 0. Or in other words, x2 is -1. Yeah, if I had chosen 1 for x3, then I would have gotten a fraction here. And I don't like fractions. Okay, that's a -1. And finally, looking at the first row, yeah, that's just -1, -1, 0. So we have this -1 here fixed. -1 times -1 is +1. So we need a +1 in the first position to get 0 here. 1 times -1 plus -1 times -1, that's 0. Okay, so that completes the third of the eigenspaces. That completes C19. Let's see if there are any questions about this.
Yes. So one question is, could you explain why once we've computed the eigenspace, this basis answers the question in the exercise? So I think that's the transformation matrix.
Oh, the transformation matrix. Yeah, I should have.
I'm not sure. Like I asked again, but then I didn't get what they meant by the question. So I think that's it.
Yeah. Okay, good question. Let's start with B, yeah, because we just did that. So for B, we basically found 3 different eigenvectors. Let's collect these here. So we have this one here for lambda equals 0. We found this one, 1, 1, 1. Then for lambda equals 1, we found this vector here, 1, 0, 1. And here for lambda 2, we found this vector here. So 1 minus 1, 2 is another eigenvector. So this is the set of eigenvectors that we found. And if you either look closely at those eigenvectors or employ the theory that I think are only doing this week, then you could see that this is actually a set of 3 linearly independent vectors. So that's the basis of our 3. So this is a basis of our 3. And that means there is a basis of eigenvectors of the matrix B of our 3. Okay, so our 3 has a basis that consists of eigenvectors of B. And if that is the case, of course, we can transform that matrix B to that basis. And if we do that, then we find that the resulting matrix is diagonal. So if we do this transformation would look like this. So transform B to this basis. The transformation would be S to the -1 BS with the transformation matrix S. And that just consists of the eigenvectors that we found in the columns. So let's just take those eigenvectors in the order that we used above: 1, 1, 1, 1, 0, 1, 1, minus 1, 2. Right, so these 3 here, those are the eigenvectors. And if you transform to this basis, then the result is a diagonal matrix. And the entries on the diagonal are precisely the eigenvalues in the order that we put the eigenvectors. So in this case, this one here, that was the eigenvector for the eigenvalue of 0. So 0 is going to be the first value in here. Then this one here corresponded to 1. So 1 is going to be in that second column of the diagonal matrix. And finally, this vector corresponded to 2. So 2 is going to be in the third column of our resulting matrix here. And the rest are, of course, zeros. Okay, so that's going to be the new diagonal matrix. And just to complete the answer for part A as well, for part A, let's not scroll back that far. Yeah, to scroll back that far, maybe I did that differently than my solution. We got the eigenvectors, that's 1, 2, 2, that's one of those. And here's the other 2. Let's just copy that. Okay, so for part A, we had these two vectors, and then another one that was 1, 2, 2. First two vectors corresponded to the eigenvalue 1. And the second one corresponded to the eigenvalue -2. Okay, so the transformation matrix that we get here is, again, we put those into the columns of the transformation matrix. And then the result of that transformation, s to the -1 as, is a diagonal matrix where the eigenvalues appear on the diagonal in the same order as the corresponding eigenvectors appear in S. So here we have those two for the eigenvalue 1 first, and then the one for the eigenvalue -2. And again, we fill the rest with zeros. Okay, and of course, if we exchange the order of eigenvectors in S, we can do that. We just have to exchange the order of the eigenvalues in the diagonal matrix correspondingly. Okay, I hope that does answer the question.
Okay, and another one. If x3 is a free variable, it happened twice. Can we also choose x3 to be 0?
Maybe you can. We usually don't, because we want to make sure that the resulting solution is not 0. And if we're solving a homogeneous system as we do here, then choosing one or choosing all the free variables to 0 will usually result in everything being 0. So that's most probably not a good choice. Yeah. So you don't do that.
Okay, that was it for questions at the moment.
Okay, great. Thank you. So I'm taking a little longer this time. I'll have to shorten the central exercise problems for the next sheet, but I think we should still discuss 110 if you don't mind. If you do mind, feel free to log off anytime. Okay, so let's go on with 110. Shouldn't take us too long, but it will put together some of the things that we've learned so far. So here we have a differential equation system with just two differential equations of the form y prime t equals 8 -1 -2 7 times y of t. And we have an initial value, y of 0 equals 1, 2. Okay, how do we solve a system like this? We already know, hopefully, how to solve a decoupled system. So a system that only contains one of these two y variables. If we had an equation that only contained y1 or only contained y2, then we could solve these systems. Unfortunately, this is not the case here. This is a coupled system. So we do have both y1 and y2 appearing here in the first row and in the second row as well. So we cannot solve this right away. What we want to do is we want to find a system that has a diagonal matrix, so that actually the system is decoupled, but pretty much does the same thing as this original system, or at least can be transformed back to this original system. And that's the basic idea that we are following here. So first thing we need to find out is this a system that we can decouple? So if we're calling this the matrix A, then the question is, can we transform this matrix into diagonal form using a basis transformation? So can we transform A into diagonal form? And if we can then use this to solve the original system. So let's go ahead. If we want to diagonalize this, then we first need to know the eigenvalues and the corresponding eigenvectors. So first thing we want to do is find the eigenvalues of A. To do this, we compute the so-called characteristic polynomial, and that is defined as the determinant of A minus lambda times the identity matrix, E2 in this case. And the roots of this characteristic polynomial are precisely the eigenvalues of A, because those are the points where this matrix A minus lambda E2 is not invertible. And then those are the points where the kernel contains more than just the zero vector. So we have an eigenvector. Okay, so let's write down this matrix here. We need the determinant of 8 minus lambda minus 2 minus 1 and 7 minus lambda. That determinant is 8 minus lambda times 7 minus lambda minus 2. And I don't see a straightforward way of factorizing this, so I just write down the expanded form. That is a lambda squared minus 7 lambda minus 8 lambda, so it's minus 15 lambda plus 8 times 7, that should be 56. Minus 2, of course. Okay, so that's lambda squared minus 15 lambda plus 54. The roots of this one can be determined by the well-known quadratic formula. So this formula, just apply that one. That is 15 plus minus the square root of 15 squared minus 4 times 54 over 2. And that is 15 plus minus the square root of, that's 225 minus 216. So 15 plus minus the square root of that difference is 9. Okay, so we get 15 plus minus 3 over 2. And that means our roots are lambda 1, 15 plus 3 is 18 over 2 is 9. And lambda 2, 15 minus 3, that's 12. And divided by 2, that's 6. So these are the roots of our characteristic polynomial. These are the eigenvalues of A. Okay, and at this point, we know we have 2 different eigenvalues. That means we can get 1 eigenvector for each of them. And those eigenvectors are going to be linearly independent. I'm talking about this in this week's videos, I think. So if you haven't watched those, then just take this as a fact. The vectors that we are getting will be linearly independent. So at this point, we know already the matrix can be transformed to diagonal form. Okay, but even if you don't know that, we still have to find the transformation anyway. So let's just compute these vectors. So that's step 2. Compute eigenvectors. And with those, compute the transformation. So we'll start with lambda 1, 9, and have a look at A minus 9E2. Okay, that is, let's see, minus 1, minus 2, minus 1, minus 2. And well, we can see that by just subtracting 2 times the first row from the second row, we get minus 1, and 0, 0. And a solution for that, we can also see that a solution for that would be, for example, 1 minus 1 or minus 1, 1, whichever you prefer. Okay, so the eigenspace for the eigenvalue 9 is spanned by the vector 1 minus 1. Second, we'll have a look at the eigenvalue 6. So we need to look at a minus 6 E2. That is 8 minus 6 is 2, minus 2, minus 1, and then 7 minus 6 is 1. So the operation this time, we just need to add the first row to the second, and we get a 0 row here. So again, we have a straightforward solution. The eigenvalue is the eigenspace is spanned by, for example, 1, 2. Okay, so we have two eigenvectors, and we can see easily that those are linearly independent, so they form a basis of R2. So we have a basis of R2 that consists of eigenvectors of A, and that means A can be diagonalized. So A can be transformed to a diagonal matrix using the transformation matrix. We're going to call this one S, and that consists just of the eigenvectors in the entries here. So the eigenvectors are 1, minus 1, and 1, 2. Okay, so that's our transformation matrix. And we also can write down the result of that, S to the minus 1 AS, the resulting diagonal. That would be 9 and 6 on the diagonal. So looks like this. So step 3, we can now transform our system so that we get a diagonal system, decoupled system, that we could then solve and transform the solutions back. So the idea here is to solve the transformed system or the decoupled system. And we do that by using a substitution. And that substitution is we'll introduce a new function z that is related to y through y equals s times z. Or in other words, s is invertible, so we could also write s to the minus 1y equals z. Okay, and that means if we look at this original differential equation, y prime equals a times y, then this means if we substitute y by sz, we get sz prime equals a times sz. Or if we multiply with the inverse of s from the left, then we get z prime equals s to the minus 1 as z. Or, as this expression is our diagonal matrix from above, that's the same thing as 9006 times z. Okay, so we've decoupled the system, means we get basically two differential equations that are not related to each other anymore. The first one is the first row of that system, set 1 of t equals 9, oh sorry, set 1 prime of t equals 9, set 1 of t. And the second is set 2 prime of t equals 6, set 2 of t. And we can easily solve these We did that in the first couple of videos in the first week. So the set of solutions for these is set 1 of t equals basically e to the 9t, so that's this factor 9 here, times a constant gamma 1 that we will later determine through the initial values. And same thing for set 2. That can be solved by e to the 6t, and again, some constant gamma 2. So that's the set of solutions for these two differential equations. And now we need to get back to our original system. And remember, we had this substitution here, y equals s set. So we just use that to get a solution for the original system. So that's step 4. Transform back and determine constants. So transforming back means we just compute y of t through s times set of t. So S was this matrix here, 1 minus 1, 1, 2. 1 minus 1, 1, 2. And the solution set that we got above here, here we have that gamma 1, gamma 2 times e to the 9t or e to the 6t. So it's gamma 1, e to the 9t, and gamma 2, e to the 6t. So we just multiply this matrix vector product here. And what we get is, in the first row, gamma 1, e to the 9t plus gamma 2, e to the 6t. And then minus gamma 1, e to the 9t plus 2 gamma 2, e to the 6t. Okay, so those are the solutions for our original system. And to determine these gammas, we use the initial values now. So with the values that we have, those were y of 0 was supposed to be 1 and 2. So we get y of 0. That means we just substitute 0 into this solution here. If we do that, we get e to the 0 everywhere, and e to the 0 is 1. So the result here is gamma 1 times 1 plus gamma 2 times 1 minus gamma 1 times 1 plus 2 gamma 2 times 1. And that's supposed to be equal to 1, 2. So what we want is a solution for gamma 1, gamma 2 that solve this equation system. So we just use Gaussian elimination once more. We have 1, 1 as the coefficients of gamma 1, gamma 2 in the first row, minus 1, 2 in the second row, and the right-hand side is 1, 2. And to solve this, we just add the first row to the second row, get this here. So first row stays unchanged. Second row becomes 0, 3, 3. And that means gamma 2 needs to be 1. And gamma 1 is 1 minus gamma 2, so that is 0. So we have our constants. And that means we have our solution. Let's see, y1 of t, remember the general solution looked like this here. And now we got the constants. Gamma 1 is 0, gamma 2 is 1. So these first parts here disappear. And there's a 1 here and a 1 here. So we just get that second part here. And that means for y1, we have e to the 6t. And for y2, we have 2 e to the 6t. And that is the solution that we get here. Okay, that concludes the discussion of 110. Again, what questions did we get?
So there's one question. Could you explain why we can write the function y like s times set?
Why we can write the function y like s times set? Because basically that is the substitution. Let me go back to the place where we actually do that. Yes, okay. So at this point here, what we do is basically we define a new function that has this property. And of course the question is, why can't we just do that? The answer is this matrix S is invertible. So we can also formulate this in this way. We can just define a new function Z through this, S to the minus 1y, and that uniquely defines that function. Yeah, and we can revert this transformation because Z is an invertible matrix. That's why we may do this. And of course, the reason why we do this is that this way we can decouple the system. We actually get our transformation so that the resulting system is in diagonal form. So basically, you just need to remember this neat little trick, and the rest is just computing eigenvalues and eigenvectors. I hope that answered that question.
Yeah, please give like feedback on whether you got the question answered or not. Like also for the chat, that makes it easier if I should answer more or not. So 2 other questions popped up while you were answering. One is, would there be 4 solutions if gamma 2 was unequal to 0?
If gamma 2 was unequal to 0, then we would basically get the same form of solutions. So that'd still be one solution for y1 and one solution for y2. The only difference would be that this solution would include both of these terms. So it would be something like, let's say, 2e to the 9t plus 7e to the 6t for y1 and something similar for y2. So still one solution for y1, one solution for y2. Just the function would look a little more complicated. There'll be examples for that on the second exercise sheet, I think. More questions?
So that was, yes, she understood it. And then there's, if gamma 2 is 1, why is y2 equal to 2 times e to the power of 6t? So that was, I mean,
gamma 2 is 1. Oh, yeah. Just have a look at this one here. So if gamma 2 is 1, then there still is this factor 2 here. That basically comes from the matrix S. This is this 2 here, from the eigenvector. From this transformation, a 2 enters this equation. And if gamma 2 is 1, then the 2 still stays. I hope that answers the question as well.
Yeah. And then a good question, really. Why is y prime the same as s times z prime?
Why is y prime the same as well? We have not talked about multidimensional differentiation yet. So basically, the idea here is y prime. Let me start this again. So what we do is we substitute y equals sz. Or in longer form, what we do is y1 of t, y2 of t, basically 2 functions are substituted by some constant matrix times z1 of t, z2 of t, 2 new functions. And now we want to compute the derivative of these functions. So let's have a look at y1 of t first. Well, what happens basically is, let's write down our actual set here. I think that was 1 minus 1 and 1, 2. It's probably easier to do this with actual numbers. So hopefully you get the idea. So y1 of t is then the same thing as z1 of t plus z2 of t, or to be a little more explicit, 1 times z1 of t plus 1 times z2 of t, these 2 ones here. And if we differentiate then, so the derivative of y1 of t is then the same thing as, well, this 1, this constant 1 just is a constant, times the function so that 1 stays in front of that function. And we just differentiate the set 1 of t and the set 2 of t. So basically every part of the sum is differentiated. And of course, the constants in front of the function stay the same here. Yeah, so basically the reason is S consists of constants only, so differentiation does not do anything to those constants. It just works on the functions that are multiplied with these constants, and those are the set functions. Okay, so that's how you compute the derivative of y1, and of course y2 works the same. I hope that answered this question. Otherwise, if not, I hope things will become more clearer through the next few weeks. And the next topic that we're talking about will be multidimensional differentiation. So we'll apply an even more general framework then.
And then there is one question about not having a calculator on the exam, and if it will be easily computable so that they can do it by hand, which I guess.
Of course, yeah. So a word of warning, things are still pretty unsure as far as the exam goes, because I just don't know whether we can hold traditional exams at all. So everything that I say is bound to change. But if we can hold the exam as planned and similar to the way we did in the first semester, then you will not be allowed to use a calculator. And of course, all the numbers that appear will be hopefully easy to compute without using a calculator. Yeah, pretty much the same as the numbers that we used here in these exercise sheets. You should all be able to do that without a calculator, hopefully. Anything else?
I had a previous question at the beginning, when you will publish the solutions or the suggested solutions for the homework problems. I promised to ask.
So the suggested solutions for sheet 1 will be uploaded sometime this week. I need to work on those a little more before I can actually publish them. But the idea is to publish them the week after the corresponding videos go online, and hopefully closer to the beginning of the week than the end. At least in the future, I try to do that. Okay,
that was it. Okay. Don't forget your poll that you made.
Oh yeah, right. I completely forgot about that one. Thanks for reminding me. So if you could still stay with us for 2 minutes. I set up a little poll, so I wanted to ask you a few questions, basically to test this feature, see how that works, so we can hopefully use that in the future. First thing I'd like to know is about problems that you may have encountered during the first week, so that maybe we can somehow cater to these problems, adapt our format to these problems. So I'll try and start this question now. It should appear on your screen, so hopefully you'll be able to cast your vote here. You should be able to choose more than one option if you want to. Seems to work, at least I'm getting some votes. Okay, I'll give you 5 more seconds if you still want to cast your vote. Most of the votes seem to be in. So let's close that first poll here, and I'll try to publish the results so that you should be able to see them. 2 major problems. First one is the course is moving too fast. And that's some feedback I also got on the forum. Thank you for that. In general, feel free to post any feedback, whether positive or negative, on the chat or on the forum, or just write me an email if you want to. I cannot see you in person, so I'm thankful for every feedback I can get. I realized the first week and probably the first 2 weeks may have been a little fast. So I'll try and slow down in week 3. And probably the main reason for that is you don't recall the necessary materials, and there was a lot of materials necessary for these first 2 weeks for these eigenvalues, eigenvectors, spaces, transformation stuff. That will be easier from week 3 on. When we're turning to higher dimensional differential calculus, basically you need to remember differentiation rules in the reals. And I do hope you will remember those. So that should require far less materials from Math 1. Okay, one more question that I'd like to ask you, let's see if that works as well, is on the length of the videos that I'm posting. So my idea here was to post a video that basically treats one piece of information, one topic. But of course, I could try to make those shorter or longer if you'd prefer that. So the question is, would you prefer shorter videos? Would you prefer longer videos? Or is the current length just right for you? So let's see if you have an opinion on that. Okay, nice to see. I'll give you 10 more seconds. Most of you cast your vote already. Okay, so let's close the vote now. And again, I'll try to publish the results. I hope you can see them. So most of you like the current length, so I'm trying to stay with that. I hope I can. I tend to make videos longer than I actually want to, but I hope I get used to that. Maybe get a little better at that as well. Okay, good to see you like that. So if there are no more questions, are there any more questions?
There is a small one about getting more exercise materials.
Mm-hmm. Getting more exercise materials. I'll see what we can do about that. Maybe I can at least post some references where you can find exercise materials. That should work. Yes. Yeah. I'll post something on the Moodle page about that.
And then also maybe we should say that the central exercises, like the recording, can be found. And then someone is asking about the slides. So yeah, so the slides and the recording will both be available on Moodle shortly. I'll have to edit the recording a little, probably, maybe download it first. I haven't tried this yet, but I will. I hope that will work. And of course, the slides, the notes that I just made will also be uploaded on Moodle. So those should be available shortly, sometime tonight, probably. And I just wanted to mention one more thing, but it escaped my mind. What was that? I at least don't see any more questions. I don't remember. Okay, so there's no more questions. I'll hopefully see most of you on Thursday for the first tutorials. So if you have any questions, be sure to pop in there. And me and a couple of other tutors will be available to answer your questions, hopefully. And again, if you have any feedback, please just post to the chat channels or to the Moodle forum. Okay, thanks a lot. We close this webinar for today.